Okay, so we're going to look at some vectors today. So basically, you guys have worked with these things called scalars a whole bunch. I'm skipping the warm-up, by the way. But basically, you guys have worked with these things called scalars a whole bunch before, which really are only like an amount of something. So they're strictly a magnitude, like 45 pounds or 60 miles per hour. Scalars are just represented by those numbers. What's different about vectors is they have both a magnitude and a direction. So something like, not only are we moving at 50 miles an hour, but we're going east. You have a magnitude of 50 miles per hour and a direction that is east. So magnitude and direction is called a quantity that is a vector quantity. And a lot of times you'll have these represented by a directed line segment, kind of like a ray, except it actually stops. So directed line segment called a vector. So you'll have what's called your initial point, where you're beginning at. So in this one, point A would be your initial point. And then your terminal point. A lot of times people don't actually draw the terminal point in, but your terminal point is where you're ending up at, where you're stopping at. So your terminal point on this one would be point B. So that line segment is a vector. You can name them with like 1 or 2 letters. That's one of the bad things about vectors is there's a lot of notation. You can write it like this. We're talking about vector AB. You can just do it like bold. Can't really write in bold, but you might see it like printed, like vector AB. So your first letter is your initial point, your second letter is your terminal point. The length of a vector represents your magnitude. So if you actually find the length of your line segment, like how far is it from point A to point B, that's your magnitude. And notation-wise, that's in like these, looks like absolute value bars around your vector notation. That's the length of that line segment. The direction is like the angle from point A to point B. So if we're talking about vectors, some vectors are equal to one another, just like some numbers are equal to one another. In order to be considered equal to one another, your vectors have to have the exact same magnitude, so the same length, and the same direction. So if you look at these are 1, 2, 3, 4, 5, 6 different vectors. Vectors A and B look like they have both the exact same magnitude, so same length, and they're pointed at the same angle, so same direction. So I'd say vectors A and B are equal. And I would also say that vector F, it looks like, is equal to those two as well. I don't think you have any other vectors that are equal to one another. So in order to be equal, they have to have the same magnitude and the same direction. You can do things like add vectors together, just like you can add numbers together. Your resultant is what you get when you add 2 vectors together, or that's what it's called at least. It's called your resultant of vectors A and B if you're adding those 2 together. So it's a new line segment that has like the combined length, magnitude, and direction of your previous 2 that you started with. So basically, how you get the resultant is if you take one vector that you have to start with, so your initial vector A, and then take vector B that you're adding to it and kind of like line it up so that the initial point of vector B starts where vector A ends, and then connect the 2 of them. That vector is your resultant, the vector A plus B. There's another way you can do it besides just like putting them like initial to terminal. You can put the 2 initial points together and make a parallelogram, and then connect your 2 vectors on your parallelogram to get your resultant that way. So instead of putting them like terminal point to initial point, you could put them two initial points together and then like copy vector B over here, vector A over here, make a parallelogram, connect the two, and you get resultant vector A plus B there. Usually I just do them the first way, but you can do either. Okay, so easiest way to, I think, sketch a resultant vector is, at least in Notability, you can trace like your vectors that you're working with and then just like copy them where you need them to go to create your resultant. If you're doing this on paper, you would have to like trace your vectors. So homework wise, if you want to take a picture of your textbook so it's a little bit easier, I'm fine with that. So E plus V, or E plus F. I went ahead and I traced vectors E and F up here. So if I'm taking vector E and adding vector F to get my resultant, I'm going to start with vector E right here. Vector F to get my resultant is going to start at the terminal point of vector E, and then my resultant that I'm going to end up with that is actually the vector I'm looking for is going to be, if I connect my initial and terminal points right here, vector E plus F is that red line that I just drew. That is my resultant. So there's the resultant E plus F. You can do the same thing with like B plus C. Oops, I did not trace vector B, so let me do that real quick here. Hey, Notability, if you turn it in a straight line, that'd be great. Nope, Notability does not love me today. Okay, it's going to be not perfect. So B and C is resultant. Could do C right here. C continues from where vector B left off. Connect the two. Make sure that your arrow is pointing the right direction when you draw these. You could erase your work in the progress, and there's your resultant, B plus C, right there. All right, other things. Every vector has an opposite vector, which has the same magnitude, but opposite directions. So say that this is your vector A right here. The opposite of vector A would be the one with the same magnitude, so act like those are the same length, but opposite directions. So that would be your opposite vector for vector A. If you put them together, add them, you get the zero vector, because you like have, if you put your first one there, and then like second one, you end up back where you started with, so it is like the zero vector. Resultant's nothing. You've gone nowhere. You can multiply scalars times vectors. A scalar product is what that is called. So if you start with like vector A and you multiply it times a scalar. So say you're just taking like 2 times vector A. That's just a vector that has the same direction but double the magnitude. So if this is 1 times vector A, regular vector A, 2A is just that vector with its magnitude doubled. So if we want to sketch some resultants down here, a little subtraction, little scalar multiplication. If you want the vector that results from doing vector E minus F, usually I just think of this as like E plus the opposite of vector F. So if you are starting with vector E, I'm going to copy this down here. Here's vector E, and then vector F, if you do the opposite of it, it's going to have the same magnitude but be opposite direction. So when I draw vector F here, I'm actually going to have it go the other way. Switch its initial and terminal points. So that's negative vector f that I just drew right there. Reversed its direction. Paste it down here. And then draw in my resultant from here down to here. Oh, yay! Finally a straight line. Good job, Notability. So e plus negative f, or e minus f, is that vector that results right there. So if you look at 2 times vector c, if you take vector c, and I basically just want 2 times it, so it doubled, same direction. There's vector c once. There's vector c twice. Just gonna erase my arrowhead and my point in the middle here, maybe. Nope. All right, shouldn't really have a point in the middle, but I can't get Notability to cooperate. So there's my resultant, 2 times vector c. You can put these vectors in the coordinate plane, and they're called position vectors if they have their initial point at the origin. So notation-wise, if the terminal point of a vector goes through the point AB in the coordinate plane, you write its vector with these, like, I don't know what those shapes are called. Sideways V brackets. And, like, the first number is like your horizontal component, kind of like your x coordinate would be in the coordinate plane, and your second one is the vertical component, kind of like your y coordinate would be in the coordinate plane. Like we talked about, vectors not only have a magnitude, but they have a direction as well. So when you draw a vector in the coordinate plane, its direction angle is the angle between the x-axis and the terminal side of your, and your vector. So it's kind of just like you're used to with angles. It does need to be the positive angle measure. So if you come up with a negative angle measure, rotate the other direction, or think about a coterminal angle. How you actually calculate the magnitude or the length of a vector is essentially just Pythagorean theorem. So think like turn it into a triangle, x squared plus y squared equals r squared. Take the square root to get r, same idea. And then you can use a little bit of trig to get your direction angle, which if you draw a picture and turn it into a triangle, you don't really need a formula for any of this. All right, so we want the magnitude and direction angle for our vector, -5, 4. I went ahead and I drew it in the coordinate plane. So it looks like that. Let's do our magnitude first. So magnitude of vector u, notation-wise, is like the absolute value. Bars is what it looks like. So if I want to figure out the magnitude, you could think of it as a triangle if you wanted to. You could think of it as like x squared plus y squared equals r squared if you wanted to. But essentially, if you think of it as a triangle, we're just finding your hypotenuse right along here. Okay, so let's just do a little bit of -5 squared plus 4 squared, and then take the square root of it. So you're going to end up with your magnitude is 25 plus 16 would be square root of 39. So magnitude of your vector is just square root of 39. So for your direction angle, I would probably just work with this little triangle that I've got going on here. And if I can figure out my reference angle, I can use that to get my angle for my direction angle. So if you think about this angle, I'll just call it angle A right there. You have the opposite and the adjacent sides. So you know that if I was to do like tangent of angle A, it's going to be 4 over -5. To get the angle, you could do arctangent of -4/5. It's going to give you like negative 38.66 degrees, because that's the interval that arctangent's defined in. But in our picture, our angle's in quadrant 2. So if you think about the angle that your calculator just gave you, it's down here. That reference angle would just be 38.66 degrees for your distance up to the x-axis. So if you want to figure out this direction angle, the screen angle right here, it's just a little bit less than 180, 38 degrees less than 180. So you could do 180 minus 38.66 degrees to get your direction angle, which gives you 141.34 degrees. So there's your direction angle and your magnitude for your vector. Last thing we're going to look at is breaking down your horizontal and vertical components of your vector. There's some formulas for it, but usually I just turn it into a triangle and use what you already know about trig functions. So I would draw your direction angle to start with. So if this is a 220 degree angle, we know that we're going to be down here in quadrant 3. Okay, so that's 220 degrees right there. Your magnitude of this vector is supposed to be 14.5. So if I draw my terminal point there, magnitude of 14.5. To break down your horizontal and vertical components, it's easiest if you just turn this into a right triangle. So your horizontal component, basically your x value, your vertical component is basically your y value. So if you think about this angle that I've got going on here in the corner of your triangle, that's 40 degrees past 220. So my reference angle that I'm working with, I could label that as a 40 degree angle in there. And then use what you know about trig functions to figure out your other two side lengths, or your x and y coordinates, depending on how you're thinking about it. So I would do, let's say you're finding your vertical component first. I'm going to call this y. You know that if you were to do, that's opposite hypotenuse, sine of 40 degrees, it'd be y over 14.5. If you multiply 14.5 times sine of 40 degrees, you're going to get like 9.320. Since I did 40 degrees, I did my reference angle. I'll actually have to think about the fact that this is in quadrant 3, so it should be a negative y value. You could have also done 220 degrees here. I just like to think about it in terms of a triangle, so that makes more sense to me to do as a 40 degree angle and then to get your negative later. You can do either. If you want your horizontal component, now we're looking for that horizontal distance, which I'm going to call x. So that's adjacent to your 40 degree angle. So I'm going to do cosine of 40 degrees would equal x over 14.5. And then multiply by 14.5 would give you x is approximately negative 11.108. Again, it gave me positive to start with, but then over here in quadrant 3 for the coordinates of this point, you know it's got to have a negative x value and a negative y value if our terminal point is down in quadrant 3. So there is your horizontal component. So if you write it as your vector, you're going to have a vector that looks like this right here.